Let's go through an example of computing a triple integral over a solid E in R3 using rectangular coordinates, the standard coordinates x, y, and z. So the function we're going to integrate is f of x, y, z equals e to the z. So it only depends on z non-trivially, but we can think of it as a function of three variables. And then our region E is a type 1 region. Now, in fact, it's also a type 2 region and a type 3 region, in fact. But we're going to consider it in this example as a type 1 region, which means that I can solve for z essentially in the bounds, which means I can find an upper bound surface and a lower bound surface for z. Now, what are those? Well, the lower bound surface for z is z equals 0, because we have that E is bounded below by the coordinate plane z equals 0, the xy plane, so that's going to be the lower bound. And the upper bound for z is this more interesting plane, 3x plus 2y plus z equals 6. So if I solve for z there, I get z is less than or equal to 6 minus 3x minus 2y. Okay, and so in the picture here, I have this upper bound is this plane right here, and the lower bound, which you can't really see, is z equals 0. Alright. The next thing we need to know are the bounds for x and y, and to find those we think of projecting this solid E down into a region in the xy plane. And in fact, it's exactly the intersection of this solid with the xy plane, and it's the triangle that we get when we set z equal to 0. So we get 3x plus 2y is less than or equal to 6 by setting z equal to 0. And of course, x and y still have to be at least 0. So if I think about where 3x plus 2y equals 6, it's a linear boundary, and when x equals 0, y equals 3, and when y equals 0, x equals 2. So I get this triangle, and with the line x equals 0 and the line y equals 0. Okay, so this is the triangle we get in the xy plane, and so that means that 0 is less than y is less than, now basically solve for y in this, and we get 6 minus 3x all over 2, and then we can see that x bounds are from 0 to 2. Okay, so now we have our bounds for x, y, and z. X is bounded by two constants, y is bounded by two functions of x, and z is bounded by two functions of x and y. So now we're ready to set up the triple integral as a iterated integral. So we have the integral from 0 to 2, integral from 6 minus 3x to 2, from 0 to 6 minus 3x over 2, and from 0 to 6 minus 3x minus 2y. The integrand is e to the z, and we've set this up as a type 1 integral, so it's dz first, and then dy dx. Alright, at this point we're really back to single variable calculus, and we just start by integrating with respect to z, and we still have these two outside integrals. And then we have the antiderivative of e to the z is e to the z, and that's evaluated from 0 to 6 minus 3x minus 2y, dy dx. Okay, so then we get these two integrals, and we're going to get e to the 6 minus 3x minus 2y, and then minus e to the 0, which is 1, dy dx. Okay, so after one iteration we have a double integral, and so we're going to integrate with respect to y next. We'll still have the integral from 0 to 2. So now what's the antiderivative of e to the 6 minus 3x minus 2y with respect to y? So basically just we have this negative 2 factor to concern ourselves with. So this is e to the 6x minus 3x minus 2y divided by negative 2, evaluated from 0 to 6 minus 3x over 2. And then we have minus y evaluated from 0 to 6 minus 3x over 2, which just gives us that factor, that term. So have an integral to take with respect to x. Okay, so we got to plug in these bounds right here. The minus sign here I can get rid of by just plugging in the bounds backwards. So first I'll plug in y equals 0, and I'll get e to the 6 minus 3x over 2, and then minus, and then I'll plug in y equals 6 minus 3x over 2, so 2y is 6 minus 3x, and so I get 6 minus 3x minus itself. So in the end, when I plug in y equals this, I get e to the 0. So I get 1 over 2. Then I have minus 6 minus 3x over 2. So after 2 iterations, we're back to a single variable integral. So I just have 1 iteration left. So the antiderivative of this with respect to x is e to the 6 minus 3x over negative 3. So I already have the 2, so it's over negative 6. And then I have minus x over 2, and then minus, well, 6 over 2 is 3, so I guess I'll just say minus 3x, and then plus 3x squared over 2, and I already have the factor of 2 in the denominator, so over 4. So all of this should be evaluated from 0 to 2. So this first term, again, the negative sign says I'll plug in the bounds backwards. So when I plug in x equals 0, I get e to the 6th over 6. And then when I plug in 2, I get 6 minus 3 times 2 is 0. So I get e to the 0 is 1. So I get minus 1/6. And now right here, this gives me a minus 1. This gives me a minus 6. And this last term here, when I plug in x equals 2, I get 4 over 4 times 3 is 3. So I get a plus 3. And then I get 0 when I plug in x equals 0. Alright, so in the end, I got e to the 6 minus 1 over 6. And then minus 7 plus 3 is minus 4. So we've computed this triple integral of f over our region E bounded by these two planes in the first octant in R3. So the main takeaway was I solved for one of the variables in terms of the other two. So in this case z, and I got my bounds in terms of x and y. And then once I do that, I look at the projection down to the xy plane, and then I think about the problem just like I would a double integral. Okay, and putting that all together, I get a triple integral, and from that point on, it's a matter of just carrying out each iteration using single variable calculus.